Good afternoon, everybody. Normally, I like to have more people in my talks. Actually, today I'm quite thankful that fewer of you have come to this talk so we can all breathe. I'm Rob Smallshire. Before I get going, I'll just tell you a little bit about myself. I think perhaps an understanding of where I come from will help you appreciate how I approach problems and the kind of view I have of the world. My background has been in software in the oil and gas sector, where I worked for 14 years. And this means two things. It means I was working with big data before big data was invented. It means I am largely responsible for the impending global climate catastrophe that is coming, and I apologize for that now. And it means I had a hand in the accumulation of the largest sovereign wealth fund in the world. There we go. I never call myself Dr. Robert, even though I am. I decided to today just because I noticed on the speaker's roster there were quite a few other doctors, and I just wanted to point out that my PhD has nothing at all to do with what I'm going to talk about. And so any supposed legitimacy this adds to what you hear from people definitely needs to be taken with a grain of salt. So, let's move on to the actual content. Our industry is perhaps almost unique in the way it is in terms of the demographics of the industry. We have a very young demographic, overwhelmingly young people in our industry. This isn't because old people forget how to write code or write bad code or can't code. It's because we essentially have exponential growth in terms of the number of people involved in what we do. And in any situation where you have that, the youngsters will always outnumber the older people. And of course, that has an effect on how much accumulated experience people have in the industry, which is actually very little. Many people in this industry, a high proportion of them have, say, less than 5 years experience and have maybe not seen systems through over the long term, over, say, 12 or 15 years. Another interesting thing about our profession, I'm going to call it that, perhaps we are IT professionals, is that many of us don't have qualifications or formal training in the field that we practice in. You can include me amongst that. My PhD is in a completely different field. It's not in computing science. Even those of you who have qualifications in computing science is about computation and computability. It's not about software engineering, right? So basically, we are in an industry of young, inexperienced amateurs. Do you disagree? You're only laughing because it's true. On top of that, we have very high turnover in our industry with respect to people and code bases. The average tenure of a developer with respect to a project or a code base is only about 3.5 years. Most code bases have lifetimes which extend much longer than that. And so this leads to a kind of collective failure to learn. And what happens then is we lose the collective knowledge that we as an industry have. You've heard a lot of things in this architecture track today from previous speakers, Simon, Rebecca, Owen, and actually hardly any of it is new, which is significant. It's all old stuff, and we need to be here to make people aware of it so that you can actually apply it, because it's good stuff. Now, in the absence of that collective body of knowledge, which we maintain, or fail to maintain, what happens? Well, actually, we fall back on what is essentially a fashion-driven approach, FDD, if you like. Sorry. Fashion-driven development, where decisions are made largely because things are cool or new, rather than for more solid engineering reasons. And in fact, it's very similar to the clothing industry, clothing fashion. insofar as the functional requirements for clothing have not changed for a very long time. It basically boils down to protection from the elements and preservation of modesty, right? But even in spite of that, we have this very high turnover where every year there are new things that we should be wearing, and it's extremely uncool to be wearing what people were wearing last year. Very much a marketing and persuasion-based industry, which appeals to our fears about not being cool. So I always like early on in a talk to give some people some advice which they can take away, and then they will have learned at least one thing. So the one thing you can learn from this slide is, as we go into autumn, layered architectures are in. So, you know, we laugh at the fashion industry and perhaps look down on it a bit from our perception of ourselves as engineers. But look at how we present and market and talk about software architectures. And the pictures are going to come up in a moment are not my pictures. They are pictures I've taken off industry websites. Everything is essentially marketed through spurious analogy, isn't it? So, monoliths. A monolith is an entirely valid architectural decision, but there's an implication here that monoliths are always spaghetti. Yeah, I really don't think that's true. Microservices seem to be some sort of protozoic life form here. Maybe that tells us something as well. And even now, I'm seeing microservices as cupcakes. Just think about that. And the arrows still aren't labeled, are they? And if you don't like cupcakes, you can always have microservice donuts. This is the pinnacle of engineering in our industry at the moment. Cupcakes and donuts. And I think that's actually tragic, that this is the way we approach things. But this is nothing new. Microservices, donuts, cupcakes, is it? This is how the technology industry works. This fashion-led approach is so pervasive in the way our industry works that people have made models of it, conceptual models. You've probably heard of the Gartner hype cycle. So Gartner is a company of essentially analysts who look at the way different industries work and write expensive reports on them. And they came up with this thing called the Gartner hype cycle, which is, at the same time, it's quite a lot of fun to think about, but I think there's a serious use for this, which we'll come to shortly. So the Gartner hype cycle says that from the inception of a new technology, we have a technology trigger, so something happens which causes some innovation to occur. And if that technology gets any traction at all, we move into what they call the peak of inflated expectations. And then over time, we realize that the hype was excessive, the solution doesn't live up to all the things that were promised of it, and quite often we very rapidly descend into the trough of disillusionment. And some technologies, as we'll see shortly, never really escape from there. And then over time, the people who stick with the technology figure out how to use it. They understand the context in which it's appropriate. Importantly, they understand the context in which it is inappropriate and decide not to use it and do something else instead. And we ascend up the slope of enlightenment, and if we're lucky, we reach the plateau of productivity where finally we can actually get some work done rather than just playing with new toys. So let's apply the Gartner hype cycle to some of the things floating around in the world of software architecture. So I'm just going to talk about architectural styles, particular ways of structuring systems. And there are plenty of architectural styles out there which have traveled this curve, some of them a long time ago. Pipes and filters, Unix command line. Very successful architecture. Layers, which are in this autumn. Plugin architectures. If you remember 10 years ago, anyone who had any contact with Eclipse RCP, Eclipse Rich Client Platform, which was this idea that you could take something that was an IDE for writing Java code and use the foundations of that to build actually, well, anything. And MVC. And some patterns, styles like MVC have traveled this roller coaster more than once, haven't they? MVC, I think, was, well, very early with Trig v. Renscal. Then showed up again in Smalltalk context. Then Apple Web Objects. Then what's next? Then we have more recently things like Spring MVC, comes up again in Ruby on Rails, Django. It's there all the time. But we're comfortable how to use it. We know how to build successful systems using it. Some things seem to get stuck in this trap. And I'm reflecting here the perceptions other people seem to have about certain architectural styles. In spite of that, of course, many successful systems have been built using this style. Some things are, I would say, just over the top here. Event sourcing, if we'd have been at this conference, what, 2-3 years ago, every other talk would have been about event sourcing and CQRS. And you wouldn't be me here, it'd be Greg Young. Right? But now if you dig around, there are people having experiences where event sourcing hasn't worked out, or they've chosen a particular technology which has taken them in the wrong direction. Where's microservices today? It's probably there, isn't it? If you hunt around hard enough, you can find some articles where people are saying, well, actually, this might not work. So maybe it's going to go over the cusp. What's down here today? Serverless is the one I chose. That's things like Amazon Lambda. That's down here. People are beginning to use this. I am going to confidently predict that in 3 years' time, you can come to this conference and there'll be a talk telling you about what a disaster serverless is in that context. So we have a model of fashion, and we can apply it to other things as well, can't we? We can apply it to practices like Agile. I place it here. You may have a different view on where it is. I like to think that software architecture practices of the type you've been hearing about today are on the way back up, and I hope this talk is part of that, as we learn to apply them in a sensible way, rather than having 2,000-page software architecture documents, which is what we were doing up here. And then some things, well, whatever you think of them, nobody's doing it. So the interesting thing about this model, even though it's fun and entertaining, is that if you're aware of it, you can use it to correct for your own cognitive biases, right? And there are lots of cognitive biases in play here. And in fact, if you look at the large list of cognitive biases which contribute to the existence of this kind of human behavior, it's very large. I'm not going to go through all of these. I'm just going to pick out a few here. So availability cascade up here. What's availability cascade? That's a bias which occurs when you're repeatedly exposed to public information. So when you go to a conference and all the talks are about microservices, that lends plausibility to that particular thing and it introduces a bias in favor of that thing. Another one, the recency effect. People are much more inclined to do things which they've heard about recently, right? So pipes and filters is a very old architectural style. It's extremely successful, but people don't do it because it's old. And that's the only reason they don't do it. Or don't consider it, rather. There are good reasons for not doing it, but they don't even consider it. What's the next one? Hyperbolic discounting. I love the name of this one. This is a bias, or a cognitive bias, where essentially your future self wishes you hadn't made the decision that your current self is about to make. Right? We discount the future implications of things. We think things are going to be better than they really are. And what's the last one? Pro-innovation bias. That's obvious, isn't it? We just like new, shiny things. So where does this leave the software architect? Well, You know, we tend to think of software architects as people who draw boxes and lines. Of course, the boxes and lines are just the manifestation of a process of decision-making, right? The structure is not the point of doing software architecture. It's not an end in itself. We're building the system to fulfill some greater need. And I'm lucky enough to do some work teaching Simon Brown's class, where one of the exercises involves designing a system. And I never fail to be amazed at the incredible complexity people manage to shoehorn into their solutions. Now, the point of the exercise is not actually about the solution themselves, it's about how you present solutions. But I am always shocked at how complicated people can make even the simplest problem. So, this is going to be the third talk today where we focus on software quality. So I'm not going to talk about structure in software architecture very much. It's very important. What I would like you to think about is qualities or non-functional requirements. There was a question at the end of the last talk about what the difference is. So there are lots of different qualities which apply to software systems, and we can think about them in advance as requirements, or we can think about them afterwards as exposed qualities, attributes of the system. And qualities are very complicated and subtle things, which makes them incredibly hard to deal with compared to functional requirements. And what I'm going to advocate for the rest of this talk, basically, is that the activities of a software architect should be directed very much, I'm going to go overboard at the end and say almost exclusively, to understanding and managing these attributes and the trade-offs between them. So just to highlight a couple of obvious trade-offs here, for example, performance can be traded off against maintainability. Right? I can go in and take some code that is quite maintainable, I can write it in a very highly optimized way in assembler, and it becomes very fast and much less maintainable. And security classically trades off against usability, right? So there are lots of complex trade-offs here, and we'll return to those. So I think the job of the software architect is to understand the qualities of the system. These two things, both ultimately just deliver calories to you, right? That's what they're for, right? But the qualities of the calories, the qualities of the packaging for the calories is actually very different, and the experiences of using these things will lead to quite different outcomes. So, deliberate design towards software qualities. And I use the word deliberate advisedly. Deliberate's one of these interesting words in English, isn't it? Because depending on how we pronounce it, we can give it different meanings. I just said deliberate design, but I could ask you to deliberate over something, and that conveys quite a different idea, doesn't it? That means, what are you going to do? You're going to think. You're going to stop, and you're going to think. Or you're going to put processes in place that give you the space and time to think about these things. So let's look for a starting point. Let's try to understand the incident forces on software systems. And I've stolen this from Grady Booch, this idea of forces acting on systems. So where do these forces come from? Well, they come from the people who are exposed to the system, right? Stakeholders, to use that word. So customers, users, business owners, marketing and salespeople. So my background is very much in product development rather than line of business enterprise computing, so I tend to worry a lot more about marketing and salespeople than the enterprise people do. However, my customers were not my users, generally speaking. Developers, testers. So these are more kind of internal stakeholders. These are people who deal with the internals of the system. So different stakeholders see different aspects of the system. And they all exert, if you like, a force on the system. And I'm going to show you some maths in a minute, but it's not real maths, it's fake PowerPoint maths, so don't worry about it. There's no actual real mathematics here. But the analogy with the forces, I think, is a useful one. And what Booch said is that the system will resolve the forces, and the net result will be zero. This is like Newton's law of software development, if you like. It's like the third law of motion here. Every force will have an equal and opposite force. And that has to be true, right? Because what would happen otherwise? Your system would just accelerate off to infinity, which isn't what happens. So the system has to resolve the forces acting on it, and it has to do that without collapsing or imploding on itself or accelerating to infinity. The incident forces will resolve to zero. So what we can do is we can, obviously, this is quite a complex picture, but we can think about factoring the forces into different groups, if you like. We can think about the functionality of the system, the qualities of the system, the constraints on the system, and principles, which is essentially, principles here is a code word for internal structure of the system, if you like. When we have a principle of choosing a particular architectural style, that is a decision about internal structure. So we can factor them into these four groups, which is an extremely useful way of thinking about software architecture. So functions, what is it for? Features, use cases, functionality. Qualities is about wellness. It's about how well it should work, right? The quality is a difficult word for a lot of people because they just associate it with kind of QA and good in a very narrow sense. Non-functional requirements is another word we use for these. Performance, scalability, security. There's a very long list of these. The constraints, cost, legal, time, money, all those things. And the principles, which I just said are decisions we make to essentially determine the internal structure. So I'm going to try and answer the question about are non-functional requirements and software quality is the same thing. We often, and myself included, use the terms interchangeably, but I think it's more subtle than that. I tend to think of non-functional requirements as inputs to the development process. They are things that go in, and I think of software qualities as attributes which are exposed by the system as built. I don't think these terms are completely interchangeable. I think one is an input and one is an output in the same way that functional requirements are an input and features are an output. These are actually quite different things. And I think you can confuse your thinking if you use the terms interchangeably in a kind of loose way. Some people will claim that features and qualities are completely orthogonal. Actually, I'll come to the orthogonality point in a minute. I just want to talk about how we deal with them, and Rebecca covered a lot of this ground, so I'm going to go through this quite quickly. Features tend to be explicitly captured. We have stories, we have cards with them on. They tend to be intentional. It's very rare for people to accidentally implement a feature. They tend to be tracked in our project management process. We know when a feature has been produced. There tends to be some deliberate aspect of design and implementation. You actually have to go and code a feature, right? You have to do some work. They tend to get tested and verified. Does the feature exist? Does it behave as we want? They tend to be documented in the user manual, if you have such a thing. And they're essentially digital. I mean binary here, really. I mean, either you have a feature or you don't, right? If the feature doesn't work, it may as well not be there. Whereas the qualities and the non-functional requirements, they're informally captured because capturing them is a real art. It's very hard to do and requires training and skill. They're emergent, and I'm going to come back to this word a lot. Rebecca used the word emergent several times in her presentation. They're untraceable in that it's very difficult to take a quality and trace that back to a particular part of the code. Right? I can normally take a feature and say, oh, this feature is implemented here. I usually can't take a thing like security and say, oh, security is implemented here, because security is implemented everywhere. In other words, they're cross-cutting concerns. We tend to deal with quality shortfalls by retroactively addressing them rather than building them into the process, because actually that's mostly because we haven't all hired Rebecca in to come and show us how to do things. Rather than testing, we tend to have to monitor for them in some way. They're usually undocumented, and they're analog quantities. They're nearly all analog quantities. Perhaps security is the counterexample there. They're also, as I said, orthogonal. So if you go back to, I guess, some of the classic software architecture textbooks, 10, 15 years ago now, software architecture in practice, they claim that functionality and quality attributes are orthogonal. So what they're saying is you can choose the quality level completely independently of setting your features. I don't agree with that at all. I think that is academic optimism at its finest, really. I think they can be at a high angle to each other, but not orthogonal. So you have some latitude in how you adjust your qualities, but that is probably going to affect how your features work. Simple example is if I take all the features away, my system becomes much more maintainable. And very secure. Yeah. So I would qualify this with ideally but unachievably orthogonal. So I think I said this already, that we very rarely accidentally implement features, right? Occasionally, users will discover new ways to compose existing features to support novel use cases, but we tend not to accidentally implement features. Right? So if you ever worked on toolbox-style software, if you're doing enterprise stuff, you probably haven't. I've worked on a lot of toolbox-based software in industry, but an example I'm going to give you is something like Photoshop, right? Where the data model is like a blackboard, and you have lots of tools which can manipulate that data. Yeah? So in that kind of software, users are continually inventing ways to use your toolbox to achieve things for which it was never designed. Right? So it's a very different kind of software from line of business enterprise software. But we tend not to inadvertently add features. Features are not emergent. Whereas I describe the qualities as being emergent from the system. And I'm talking about the qualities here, not the non-functional requirements, the outputs from the system, the characteristics of it. And it turns out that emergent is actually quite a recent word in English. It's not a... It doesn't go back 1,000 years. You can't find the word emergent in Norwegian or Greek or something, right? You have to go and look up its coinage. And I don't normally read quotes to you, but I'm going to read this one. So this is from George Henry Lewis, who was a philosopher, 19th century philosopher, mostly famous for being married to George Eliot. George Eliot was a woman. But while he was philosophizing, he thought about emergence. And he said this: every resultant is either a sum or a difference of cooperant forces. Their sum when directions are the same, their difference when their directions are contrary. Further, every resultant is clearly traceable in its components. That's that word I used. We can trace features back, can't we? Because to code, because these are homogeneous and commensurable. There's a word we don't use very often these days. It is otherwise with emergence, when instead of adding measurable motion to measurable motion, or things of one kind to other individuals of their kind, there is a cooperation of things of unlike kinds. The emergent is unlike its components insofar as these are incommensurable, and it cannot be reduced to their sum or differences. That's quite dense, but I've highlighted the last sentence here. It cannot be reduced to the sum of their differences. He may not have had the vocabulary for this at the time, but what would we call that? We'd call that a nonlinear system, wouldn't we? It's a nonlinear system. It doesn't work by addition or even multiplication. And what do we know about nonlinear dynamical systems? We know that they are hard to predict, they're harder to model, and they're very hard to manage, nonlinear dynamical systems. Has anyone been to a talk at a conference recently and seen this picture? It's very common to see this. It's usually, shortly after you see this picture, somebody will say, emergent. It's usually somebody who works for ThoughtWorks. Sharp intake of breath there from part of the audience. So, where are we there? So a good game to play is to take this notion of hard to model, difficult to predict, impossible to manage systems, and use that phrase, which is a bit of a mouthful, and replace it every time you hear emergent, right? So if anybody says emergent design, what they're actually saying is hard to model, difficult to predict, impossible to manage design. Because emergent is, by definition, and we went back to the original coinage, non-linear, dynamical system. So actually, when anyone says emergent, they really mean accidental design. So let's look at how properties emerge. We have an agile process, so any process, but an agile process, as we've heard, is basically a machine for pumping features into systems. That's what it does. It just inflates systems with features, right? On a cadence of days or weeks, right? But qualities take time to emerge, right? Usability, maintainability, scalability, all of these things take time to emerge from the system. And so they emerge over months and years. And then we detect them, we see them, we sense them in the built system. And we have this kind of delta of wellness. It's the difference between how the system is and how we would like it to be. And what happens to our wellness delta? It gets encoded in a very complicated encoding into defects, which then go into an infinite capacity priority queue called the bug tracker, and gets sent back round again. Which is a problem, because this is like having, if you think about this in signal processing terms, this is like having an incredibly brutal low-pass filter on your feedback loop, right? Those of you who've done any signal processing. This is our feedback loop, and it's heavily filtered for the long term, which is a problem if you want a responsive control system. So I just want to point out here that software architecture really needs to facilitate how these things are done through principles with deliberate design for, obviously, within the constraints and for the qualities. I think Winston Churchill said it better than me. He said, however beautiful the strategy, you should occasionally look at the results. And the reason that working with qualities is very hard is because they trade off against each other, right? As I pointed out earlier. Performance versus maintainability. And because of these trade-offs, we have a very complex fitness landscape. The objective function, the thing we're trying to optimize for, is actually really complicated. It has a very challenging shape, and navigating around it and trying to find the global optimum here is very difficult. We tend to get stuck on local optima in the quality space, if you like, because the cost of hopping to an adjacent peak is very high, and we're not allowed to regress on any of these qualities ever, right? So it's basically a hill climbing algorithm. It's very difficult to find a good, if not the global maximum, a good maximum in this space. And of course, this is just a two-dimensional space, which is complex enough, right? But how many qualities do we have? A large number of qualities. And so, I mean, I've worked on actual high-dimensional optimization problems in various fields, and you run into this problem called the curse of dimensionality, which basically means that your parameter space that you're trying to search is just vastly complex and impossible to characterize. So, actually, the job of the software architect is really difficult, isn't it? We're basically asking them to come up with solutions which deliver certain qualities in a highly non-linear dynamical system, which we can't really say very much about at all. It's really hard. I try not to have too many funny slides, but we talked about features and agile earlier. Several people have brought this point up. And I like the crane picture, because how do you solve this problem with cranes? You have a bigger counterweight, right? Well, actually, you have a better crane driver, would be the one way, but you could have a bigger counterweight on the crane. So we can actually make this system better by adding mass to it, right? We can make, which, adding mass to things adds inertia and tends to make them slower. But actually, I think that's what software architecture is about. It's about adding some inertia and mass to the process so that we have time to slow down and think, right? This is hard stuff, and it requires constant attention. So these are cartoons. Don't take the quality levels I've set on these things terribly seriously. They are literally cartoons. But what I want to highlight is the fact that we have a lot of choice in how we build these things. My Twitter app on my phone has essentially identical functionality to the Twitter web app, right? Supports essentially all the same use cases. Okay, it has different qualities because I can carry my phone around more easily than my desktop computer. But of course, there are different qualities here which are important to us. Portability might be higher on the web app. We can move it to different types of system, whereas portability on our native iOS app is, well, it's pretty much tied to iOS, isn't it? We probably have to rewrite it to go to Android. Maybe the contrast is clearer if we just consider a mobile web app versus a native mobile app, right? Identical solutions. In fact, you can do this with Twitter right now because you have the choice, right? You can go to the mobile app or the web app. But of course, they have very different qualities attached to them. So we have a lot of choice, actually, when we're choosing architectural solutions to get ourselves to the right part of the quality space, if you like. So I want to highlight cupcakes, remember? I want to highlight the fact that when we choose an architecture, we are making a decision about where to place ourselves in software quality attribute space, right? And that should be the main driver on how we choose the architectural style we're using, not because microservices are fashionable, but because microservices have all the right qualities. So, very high deployability, right? We can deploy parts of the system very easily. I would say the operability is very low. You need a shit-hot DevOps team to make this work, right? So the operability is a big challenge here. And of course, that's a trade-off you're making, right? If we're all very quiet now, we can hear Simon Brown sobbing at the back at these architecture diagrams. Do you know why? It's not the cupcakes. They're not labeled. Yes, I talked about doctors of philosophy at the beginning briefly, didn't I? Here's another doctor of philosophy. Has anyone read this particular PhD thesis? Come on, somebody. Yes, of course you have. Oh, yes, we know who as well. So this is Roy Fielding's PhD, which is basically where he described the architectural style we now know as REST, representational state transfer, right? And I haven't read the whole thing. I've read enough of it to actually go back and figure out what he actually defined REST as, rather than what the rest of the development community defined it as. But on reading through it, you come across some quite nice phrases, I think. You only have to go to page 15 to find this one. Some architectural styles are often portrayed as silver bullet solutions for all forms of software. However, a good designer should select a style that matches the needs of the particular problem being solved. It is your responsibility as a professional architect or software designer to correct for the Gartner hype cycle in your decisions and make decisions based upon essentially sound engineering practice and the best state of knowledge we have. Fielding refers to another book, which is actually a book about building architecture, which is extremely hard to get hold of. But there's a nice quote in there as well. Personal stylistic concerns have no place in the work of the professional architect. I'm going to cover a little bit of the same ground here about how to fit management of qualities into an agile process. I guess most people are engaged in a process that is at least nominally agile, if not actually responsive. And, here's the kind of classic Kanban board view, to do, impeded, doing, done. This works very well. This is largely how I communicate with my wife these days, through one of these on a Trello board. This is how we run our household. It's extremely effective. And one of the ways, and Rebecca mentioned this, of building qualities into a process like this is to look at the definition of done. What does it mean for something to get to this last column? What does that mean? So if you go to Mike Cohn's, chief Scrum Master in Chief, I suppose, his website and look at his definition of done, it's actually pretty thin, I think. It's incredibly thin. It says almost nothing about how to build good software, really. Then again, neither does Scrum. So, the code is well written. It's been checked in. Wow. It was pair programmed or reviewed. There's tests at all appropriate levels. That's an incredibly vague thing, isn't it? And the feature, see, it's very feature focused here. The feature the code implements has been documented. So one approach here is to try to build some quality check into the definition of done. And you could go with the checklists. If you haven't read the checklist manifesto book that was being recommended in the previous talk, you must read it. It's wonderful. So people try to build some quality checks into this. And I've tried this. And I have to admit, I tried this and it didn't work very well. Because what happened was this. And, you have a column after that, which is like, are we there yet? And things just pile up, and we just add columns because, it's been performance tested, but it hasn't been tested for security yet. And basically, we have a column per quality gets added to the board, and we never actually reach the end. It's like Zeno's paradox. So I think, and because the qualities emerge over the longer term, I think monitoring is the way to go. Where we can monitor, we should monitor. There are different ways of doing that. Owen this morning was talking about essentially getting telemetry from the outside world in an automatic way and using, perhaps some almost data science approaches to analyze that and to control how we understand our system is being used. Some of these are more challenging. Portability is an interesting one. I mean, how do you monitor portability, right? Well, you could do what Apple did. When remember Apple moved from, when Mac OS was first written, that was around the time of the move from 68K to PowerPC, right? But very early in that process, Mac OS, Darwin, was being built on Intel processors, right? All the time, Apple had an Intel version of Mac OS, basically for as long as Mac OS has existed. Right? They didn't deploy it to anybody, right? So that's how you can mitigate against these things by using other strategies. When monitoring doesn't work, then you're going to have to do something that we all need to get better at, which is actually go and talk to some people. You need to get out and get away from your computer, go and hang out with people, go and talk to the stakeholders. Find out what their actual experiences are. And of course, depending on which qualities you're interested in, depends on which particular stakeholders you need to go and talk to. So in addition to these, I think it's a useful and valuable exercise just to think about who all the stakeholders of your system are. And you'll probably find they're much more diverse than you think you are when you think, oh, I've got 3 stakeholders, and you end up with 20. And I think 20 is probably about the right number. One group of people you really must go and talk to is the people who support your system. They are a gold mine. If you're an architect, just go and hang out with the support folks while they're sitting there manning the phones or the email help system or whatever you're using, right? Just spend a day with them. Find out the problems they're having. Because they're papering over all the cracks in your system that you never get to hear about because they're papering over the cracks in your system. All right? Spend time with them. Extremely useful people. So, yeah, depending on what you're interested in, obviously the functionality, development and maintenance costs, some of these things are internal. Obviously, architects and designers and analysts and developers, they're interested in those internal things. Obviously, external stakeholders like users are interested in things like usability, but quite often the people buying the system are not interested in usability. They're quite happy to inflict it on the people who have to use it. So go and talk to these people. So I think I just have a couple of minutes.
No, actually you're...
Am I over? Right, I am done now. I am gonna finish right now, okay? I am going to finish by saying that I think a good starting point is to have software architects essentially be champions for software quality, software qualities in their organizations. And a piece of advice that was given to me a long time ago and has stood me in good stead, as they say, is that as a software architect, if you look after the quality attributes, the features will look after themselves. What does that mean? It means everybody else in your organization is worrying about features. Project managers, developers, analysts, everybody else. If all you do is think about quality attributes, that's fine, because there are plenty of other people who will make sure the features get built. Thank you very much.